like to talk about some achievements of technology regarding the pixel technology. Actually, okay. The outline of the presentation is as follows. I'll introduce some pixel shrink history for higher resolution, and next three would be to explain about the electrical performances, pixel performances, and the next three items would be about the optical technology. So why we are develop the better pixel is that the one of the purposes would be to make high resolution sensor. So because the sensor size is limited, so we should shrink make pixel size smaller. But it is easy to understand that if we shrink a pixel, then the performances will degrade. So in order for small pixels to have the better performance, in order to make the better 100 megapixel or 200 megapixel sensor, then we should make the basic pixel performance better. Better basic performances would be, for example, like better sensitivity and the higher full well capacity and lower noise. So that would be the basic performances the smaller pixel should have. So we developed the CIS CMOS image sensor from the early 2001, and already passed 20 years and more. And then we can see that the pixel size has shrinked by more than 1/10. So the area scaled down by 1/100 for higher resolution. So we developed 108 megapixel sensor, and also recently we developed a 200 megapixel sensor. In order to realize at high resolution sensor 12 mega resolution, so we had to apply 3x3 array and also the 4x4 array for a 200 megapixel sensor. So suitable architectures and the technologies were tried and have been developed to optimize the high resolution sensors. So I'd like to talk about a little bit, talk about this. The first is that after the innovations which happened in the pixel history, it was in the morning session. It was already explained that for example, BSI and also the DTI was the next innovation in pixel technology history. So actually, we at the beginning we tried two kinds of technologies at the same time, BDTI and FDTI. And also each has its the better points for each technology. But we've got to know that for smaller pixels, the FDTI technologies are much better and have many advantages. So first of all, the FDTI structure enables the much larger PD capacitance, which leads to the much larger full well capacity. So because the FDTI means it has two meanings at the same time: full DTI or front DTI. So the DTI physically isolates perfectly between adjacent pixels. So there's no blooming between adjacent pixels. So it is one of the reasons to realize a very large full well capacity. And also because of the FDTI also enables the very large PD capacitance, and we can use the full silicon volume as make it as the depletion region to have very large PD capacitance. And also the PD is the buried deeply, and it is very broad. So we can make the transistor size larger. And also the one very important additional good point of the FDTI is that it ensures sensitivity and crosstalk at the same time when it is combined with the BSI. So, but if we kept the FDTI technology same, then if we as we shrink, if the pixel size shrinks, maybe full well capacity would have been decreased, like this line, red line. But we tried to keep the same full well capacity per pixel as the pixel shrinks from 0.8, 0.7, and down to 0.56. So we can see that all of the smaller pixel generations have the same level of keeping the same level of full capacity per pixel. How it was possible is that for example, when we went down to 0.64, in order to keep the silicon PD volume, we made the DTI size smaller. And also when we went down to 0.56 from 0.64 pixel, we applied the three techniques at the same time. So FDTI CD critical dimension size was decreased by 10%, and also we decreased the p-doping, and also increased the endoping at the same time to make the full one capacity at the same level. So at the beginning, I explained that we have searched for the optimized structure for 50 mega and 200 mega sensor based on FDTI. That is the novel DCC structure. The novel pixel structure, which is called DCC. Actually, this is the kind of a structure based on structure. DTI center cut. It was a device for basically for improved noise performance. So we are here two pictures are compared together, and it is the previous structure, and this is the DCC structure. So the FDTI surrounds perfectly one single pixel. So it is inevitable that the four FD regions are separated physically. So it is also inevitable that the area of the FD would increase when we are to read several pixels together like binning. And also, as the pixel shrinks, we have to the number of sharing pixels larger. For example, like 4 shared to 8 shared. Then, for example, when we are to realize the 8 shared pixel, then the wiring model will be very complicated and complex. So this makes the FD capacitance even larger. So it results in the lower conversion gain. So lower conversion gain, as you know, makes the dark random noise larger. So in order to solve this problem, we made this DCC structure. DCC structure, the 2x2 pixel, the center of the 2x2 pixel, the DTI is cut. And here, we can merge 4 separate FDs into this small area. So the size of the FD area is effectively decreased, which makes much smaller the FD capacitance. And also the number of contacts are decreased by a quarter. And the connection metals are getting much simpler. So the parasitic capacitance gets even smaller. That makes the at least 50% larger conversion gain, and this enables the dark random noise less than 1 electron, even at high resolution sensor. And also, this structure has one additional very good the advantage. Recently, there are many sensors which they adopt the 2x2 OCL for the 100% PDF. So in this case, for example, you can see that the micro lens focuses onto the cross section of the DTI, so it makes some optical loss or a larger crosstalk. So if we can the micros can focus onto the DCC area, then we can reduce the optical loss effectively. And you can see that the comparison of the non-DCC and the DCC structure, the QE performances. And the upper graph shows that the CG conversion gain improvement according to when we apply the DCC structure. And also, we are heading for we developed dual VTG technology. Actually, when we adopted the FDTI first time, the photodiode depletion region is buried deeply under silicon. So in order to transfer charge effectively from PD to FD, so we had to develop the VTG structure. VTG represents a vertical transfer gate. But when we are to increase full capacity larger, we found that the transfer margin of the single VTG, the previous VTG, is kind of some less margin, and the optimization points is very narrow. So we had to resolve this problem to keep large the full well capacity per area. So we added the VTG one more to it looks like a little bit like FinFET structure. So the two VTGs work together. Makes the potential gradient, which is electric field from the deep photodiode to FD, much better, smoother. So it makes the transfer efficiency much better, and as you can see, for the pixels with the dual VTG, as we lower the TG high voltage, the image lag does not increase. So it means it has much more margin. So we are in this table, we are comparing the single previous VTG and dual VTG, the performances. Actually, the direct effect of the dual VTG is that they increase the full well capacity. We can keep the transfer efficiency, which is one the metric is the image lag, would be kept at the same level or better at the same TG high voltage. Or we can use this dual VTG technology as we can keep full well capacity at the same level, and we can reduce the TG high voltage. And actually, the reduction of the dark random noise would be due to not because of the dual VTG, but due to the application of a DCC structure. So the combination of the DCC structure and the dual VTG would be the future direction of Samsung image sensor, which fits very well with the 200 mega or even higher resolution sensor, and also including the 50 mega sensor. So I chose the pixel dynamic range as one metric to observe the trend according to year. So we categorized into the BDTI and the FDTI plus the VTG, single VTG, and finally FDTI DCC plus the dual VTG. So we can see that as the full well capacity increases, the pixel dynamic range increases in the FDTI. And as I explained already, the FDTI was also technology has evolved. For example, CD was increased, and also the effect of the larger full well capacity and the dual VTG, the dynamic range increased a lot compared with the previous generation. Next, I'd like to talk about the evolution of the pixel optics technology. Actually, we focused on the reduction of optical loss and thus improve sensitivity. So I'm describing the change of the pixel optical structure from the first generation to fourth generation. But what I want to say is that this conventional pixel technology, the increased improvement of the sensitivity is limited. It is very difficult to improve more. So the nanoprism technology would be the one very good candidate for much better the optical efficiency. So I'd like to talk about nanoprism technology here. Nanoprism is basically using the diffraction phenomena. For example, we can control the phase delay when the light passes through this layer by controlling the size of the higher Ri material. So if we design the CD, the size of the pillars very well, then we can route the direction of light according to wavelengths. So the result of the nanoprism technology is here. Then we can see that the most important thing is that the optical efficiency was improved more than 25%. And according to this result, the measurement of a QE was greatly improved. So actually, there is some kind of when we measure the QE directly, it reaches almost 100% QE because it collects light from adjacent pixels. So I chose the YCSNR and the sensitivity per area as the pixel optical performance metric. So we can see that as we advance from the first generation to first generation, the YCSNR and the sensitivity is improved, but it is seen to be limited. It is very difficult to surpass some line. But if we apply the nanoprism technology, we can see that the great improvement is achieved. So I talked about the recent achievements and the future direction of the pixel technology, the electrically and optically respectively. So the conclusion is that so FDTI structure enables a larger PDA capacitance per unit area, and some technology also is now evolving. And DCC structure combined with the dual voltage will be the future direction for high resolution sensors. And pixel optics technologies were developed to reduce optical loss, but has limitation. So the nanoprism would be the very good candidate, future candidate for overcoming this limitation. Thank you.